The only way I can think to bound it in the other direction is to provide something that we want to do. I guess I can answer this. So before I get into that, I'll answer this. What is Hypergeometrica? I did a live stream which is recorded yesterday on it. Hypergeometrica is supposed to be an open source project to compute the hypergeometric function in a distributed fashion. So if I want to compute 1 trillion digits of pi, and you have a supercomputer at your disposal, what software would you use? I want to write that software. Now when I say supercomputer, it can be any network of computers as long as you can distribute the work across multiple nodes, so to speak. So Hypergeometrica is something that can do distributed computation of mathematical constants or functions and so on. That's kind of the short rundown of it, I would say. So, let's see. Maybe I shouldn't try to bound my word length. I mean, my word length is already given. So actually, I'm kind of going down a rabbit hole here. Let's go back down and write this out. L is plus 2. I didn't even write L. I wrote 2. L plus 2b minus 1 is less than W. Well, our word length is either 32 or 64 bits, so really I shouldn't have written this thing up here. This is kind of bogus. I mean, it's not wrong, but, well, maybe it's wrong. I'm using Lisp. This code right here is all Lisp code. Of course, whoever runs the code doesn't need to know it's Lisp, but yeah, it's all Lisp. So let's assume a 64-bit platform. Then we can establish that L plus 2b minus 1 is less than 64 bits. This means L plus 2b is less than 65. Let's assume we're trying to find a suitable transform length. Then we have L is less than 65 minus 2b. Okay, so let's write this up here instead. That let's first note that W equals 64, and L should be bounded above by 65 minus 2b. So to bound it below, we actually need a something that we want to compute. I mean, L can be 0. I mean, we know that L is greater than or equal to 0. I mean, that's a trivial bound, I would say. So L is greater than or equal to 0. But that doesn't really tell us enough. We want to know kind of what should L be minimally so that we can achieve some sort of goal. So let's say we want to do billion-digit numbers. Then that means our numbers are going to have 10 to the 9 digits, decimal. That means the maximum representable number is going to be 10 to the 10 to the 9. Actually, 10 to the 10 to the 10 to the 9 minus 1, but we'll just keep this. And the maximum representable number in our system with log base b and log length L is going to be 2 to the b, 2 to the L, minus 1. Where did I get this, by the way? If we have a number in base b, then that's the same thing as a sum of numbers, the coefficients xi times capital the maximum coefficient possibly is b minus 1, so let's just assume all the coefficients are b minus 1. Then this equals the sum of b to the I plus 1 minus b to the I. This series telescopes, so we have the sum b, oops, ignore that. We have b to the, let's say this goes up to n, b to the n minus 1 plus 1 minus b to the 0, and this equals b to the n minus b to the 0, which equals b to the n minus 1. So this is where this came from. Our base is 10, our n is 10 to the 9, so our maximum representable number is 10 to the 9 minus 1. I don't think I mentioned that, but there's why I chose those things right there. Yeah, that's kind of it. So the sum for pi is indeed something like that. The sum for pi is something like -1 to the k. What is it? It has like a 3 or 6 factorial in it. Oops, it has an 3k factorial. Okay, it's like 1359140 plus 545140134. So, you know, over something with like 6k factorial. Oops, factorial k. I don't know what it. I don't know. There's some other things with a 640 k plus 1/2 or something like that. Anyway, yes. So there's a big sum. This is like 1 divided by pi equals 12 times that. So yeah, we have this big computation here, and we want to distribute those across the nodes. This, in your example there, this is the A, B, C, and so on and so forth. What I'm specifically working on is, okay, so we can, if we want to distribute these across the nodes, we need to divide the work up in an even fashion. But if we want to divide it up evenly, if pi equals, let's use the terminology that you used. Let's say pi equals equals a plus b plus c plus so on and so forth. A really simple approach might be to say that A goes on the first core, so this would be core number 1, this would be core number 2, so on and so forth. But the complexity of calculating each of these things changes as time goes on. So what I'm trying to come up with is a measure of the complexity of sorts of each of these elements, so that I can say, well, let's say pi equals, again, a plus b plus c plus d plus e plus f plus ... Maybe these three have approximately the same computational work as these two, which approximately has the same computational work as this one. So we'd assign all of these to core number 1, these to core number 2, and this to core number 3. So in doing all this math that I've been doing in this video so far, I've been trying to find out, in the end, what is the maximum possible representation of. It scales approximately linearly. It's about it's something like n times log n, where n is the nth element across here. It's definitely not exponential. So this right here is not accurate. But more importantly, I would say is, so even if it does scale linearly, let's say this is approximately linear here, then we might naively say, okay, well, then let's take 5 of these, take another 5 of these, and let's put those on, or 3 here, and 3 here, and 3 here. and let's put 3 per core. But how do you determine if it should be 3 or 5 or 100 or whatnot? The way to determine that is to figure out what is the size of each individual computation. And that's what I'm trying to do in a very generic sense right now. It definitely isn't random, and it definitely is increasing over time, but it's increasing at, it might be log cube n or something like that. I think to compute pi to n digits, it's log n times log, not cube here, it's cube here. Yeah, I don't know. That's what I'm trying to figure out, is put a bound on the size of things so we can do them maximally efficiently. I'm looking to optimize, in a mathematical sense, optimize the size of the work units for each individual core or machine. I hope that made some sense. Good. All right. So if we want to represent a billion digits, if we want to calculate a billion digits of pi, then we have this, these negative 1s cancel out, we have 10 to the 10 to the 9, we can log both sides, so this would be 10 to the 9, 9 log 10, which is less than or equal to b times 2 to the L. If we log this again, we get 9 log 10 plus log square 10 is less than or equal to log b plus L. This is a constant over here. Let's see what it equals. So let's look at plus. First, let's define log. Defun. I typed it all today. Defun log of n is, or x is the log of x base 2. X base 2. So let's do this. Plus times 9 log 10. And that's added to the log of 10. Now we get 31.629. So this is about 31.62, and that's less than or equal to log b plus L, which means that L is less than or equal to 31.62 minus log b. Well, this means L is bound below by this. So this is our other inequality up here. So we have 31.62 minus log b is less than or equal to L is less than or equal to 65 minus 2b. So so now that we have inequalities, we can solve this inequality in various ways to find satisfying. Let me rearrange some of my stuff over here. We can solve this inequality to find applicable values of b and applicable values of L. Some other little trivial constraints is that b must be less than or equal to 2, which is less than or equal to 64. So this is one. Can I undo? I hope this thing has undo. Yes, it does. Let me choose a different color. So here's one of our constraints. Another one is right here. L is going to be, let's see, L is the transform length, so technically it's unbound, but let's see. I'll just keep it. Let's say L is unbound.